This video is about Hooke's law. This should be a revision from GCSE hopefully, but just make sure that you're clear on everything, and there's one or two bits that go a little bit beyond what you did at GCSE. So we need to know about how a spring stretches when you apply a force, whether or not it's a linear relationship. We need to be clear about a thing called the spring constant, and we're just going to mention quickly how the rubber band compares to that. So here's our spring, we've applied a force to it, and it's stretched with an extension of delta L. If you do this experiment, what you will find is that the extension is proportional to the force applied. And the constant of proportionality is called the spring constant. Okay, so this is a constant for any given spring, and it tells you how hard the spring is to stretch. Hopefully you can see from the units that this is in newtons and this is in meters, so the spring constant unit is newtons per meter. If you think about that, then that helps you quite a lot, because if you say, for example, that a spring constant is 50 newtons per meter, then what it's telling you is that you'll need a force of 50 newtons to make the spring 1 meter longer. Now, of course, it might not stretch a meter, but it's a proportional relationship, so a force of 5 newtons will make it 0.1 meters longer, and so on. Okay, of course, all this only applies as long as we go up to the elastic limit. Once you go past the elastic limit, then the spring won't go back and the extension is no longer proportional to the force applied. Okay, so here's our graph. This is the force and extension for reasons we'll look at later. It seems like it's sort of plotted the wrong way around. You'd normally think I'll put the force along the x-axis, but there are reasons for this we'll come to later why it's plotted this way around. Initially straight up to the elastic limit. Once you go past the elastic limit, the graph starts to curve and the spring will never go back to its original length. If we compare this to a rubber band, you might imagine rubber bands stretch just like springs do, but in fact that's not the case. When you load a rubber band, you add weights to it carefully, making sure you don't drop the weight on, then you get this curve. If you take the weights off again, then you get this curve, the unloading curve on the way back. And what you'll notice is that the length it's stretched to is longer. So if you understand the way this graph is, this is how far it's stretched going this way. So if you put, say, 10 newtons on a rubber band, but then you go back down to only 6 newtons, the rubber band stays much longer than it was when you'd lowered the 6 newtons on in the first place, which I think is quite surprising, but tells us interesting things about the way rubber bands stretch. It also tells us about the energy that's in bands that we'll look at later. Okay, so a couple of examples just to see. So you've got a 0.38 meter long spring. It's stretched by a force of 2 newtons and stretches to 0.42 millimeters. What's the spring constant? So the key thing is here we're looking for the extension. So it doesn't matter how big these numbers are. What matters is the difference between the two numbers. So it's stretched by 0.04 meters with a force of 2 newtons. Okay, so to work out the spring constant, we do 2 divided by 0.04, which is 50 newtons per meter. If the spring constant is 25 newtons per meter, calculate the extension when it's the tension is 10 newtons. So hopefully you can see from that that's a lot less than 25 newtons, so it's 2.5 times smaller than 25 newtons, so it's 2.5 times less than 1 meter, which gives you 40 centimeters or 0.4 meters of extension. You could put the numbers into the equation, of course, for that. The tension in the spring when it's extended by 0.5 meters or 25 newtons will stretch it a meter, so to stretch it half a meter you'll only need 12.5 newtons. Okay, as ever you can just rely on the equation, but if you understand what this means, that will save you a lot of problems and give you a more sort of common sense answer. So we can now look at what happens to the spring constant when we have different arrangements of springs. Okay, so here's our one spring. Well, what about if we put 2 springs, and we would call that in series, one below the other? And what would happen if we had 2 springs in parallel? Okay, side by side. Okay, so we can look at these different arrangements and see if we can work out what the spring constant of this system would be, given the fact that all the individual springs have this constant of this one spring here. So if we do it in parallel, we've got our weight here applied to two springs, A and B. Okay, and we can say for spring A that the force on A is the spring constant of A times its extension, and the force on B the same. These delta L's must be the same for both springs, okay, because we've pulled it down the same amount. So the combined weight on the two springs, the weight is the force on A plus the force on B because it's in equilibrium, which means that's Ka delta L plus Kb delta L, which gives us this new spring constant, the spring constant for A and B put together in parallel. Okay, and the way we can do that is to see that this is Ka plus Kb. Now, they'll always just give you two springs that are the same as each other, but hopefully you can see if you had, for example, two springs with a spring constant of 50 newtons per metre and you put them in parallel, then the total effect would be 50 plus 50 is 100. You can see, I hope, that pulling two springs in parallel will be twice as hard as pulling a single spring. If we do the same for a series arrangement, okay, now both of these are taking the weight of W. Spring A doesn't really kind of know that spring B is there. If you put this weight straight onto spring A, it would have the same tension in it. So spring A will stretch just the same as before, spring B will also stretch, it just thinks something's holding it up here. So they'll both stretch the same. So the change in length for A and B is the change in length of A plus the change in length of B, which means that W divided by the spring constant for the two springs is W over Ka plus W over Kb, okay, which means 1 over Kab is 1 over Ka plus 1 over Kb. Now again, this looks quite complicated, but they'll only ever give you two springs with the same spring constant. So if these were two springs with 50 newtons per metre, we'd have 1 over 50 plus 1 over 50 equals 1 over 25. So the spring constant for A and B will be 25. Effectively, it's twice as easy to stretch two springs like this because each one is stretching. So if you want the force you need to stretch these two springs by a metre, all you've got to do is stretch A by half a metre and B by half a metre, so that only takes half as much force.